So the title of talk, as it says, is an unsophisticated look at curvelets and how to use them for seismic data processing. The title says something that looks like the presenter would be me, kind of find this curvelet sophisticated at first. So, and it was like, and I realized later on, and talking to other people, I realized that everybody says, oh, I don't know what these curvelets mean, I don't understand them. So when I was done with my PhD, I did interpolation with the Fourier transform. I said, I had this time, I said, oh, I'm going to look at these curvelets and see what they mean. So I wanted, and I realized that looking at all the literatures around, I realized there's not like representation, there's no graphical showing of these curvelets, what they mean. So I tried to go panel by panel to these curvelets and see what they show from simple seismic sections. And by gaining this understanding, I later realized that, oh, these can be really useful and I can use them for other purposes that I'm going to show you today. So the talk, I'm going to start with some little introduction. I will keep them really short. And then I will say what the curvelet transform is. I avoid lots of mathematics. This is really heavy mathematics to it, but I will try to avoid those, but just show the main points, what they mean. So I'm going to use this transform for interpolation of seismic data, and I'm going to show you some synthetic and real data examples of those. And some ground rule elimination lately that I realized that I can use them for that as well. And some conclusions at the end, that little short slide. All right, this is my introduction, curvelet transforms. So I'm trying to put as short as I can. Curvelet transforms are FK filtering integrated with frame and operator theory. There's nothing more than that. But it needs lots of details. If you go to this frame and operator theory and look at their books, there's lots of mathematics. There's lots of conditions you need to satisfy. Luckily, Fourier transform has it built in it. But if you are trying to do in small windows that curvelets do, you need to deal with lots of orthogonality problems and these things that all arise with this frame operator theory. So I'm putting this fine print here at the bottom to kind of keep myself away from this thing that I'm not going to talk about this part. I'm just going to just focus on this FK filtering part and show how I gained this understanding and this things that I think curvelets can be considered FK filtering. So this makes it easier to understand the talk, and we can gain the physical understanding that I want from this talk. All right, let's say another thing. The curvelet transform is introduced, the main guys that famous for developing it is Candace and Donoho. And this is the website that you can go there. They have all their papers. They have their MATLAB codes and C codes for research purposes. So you can download and look at them. But inside, so these guys introduced it, and it's a really useful thing that these guys put it as free, and anybody can go and try them. And in fact, lots of people in the seismic industry researching in the universities, they try to look at these and use them. So they used it for interpolation in the UBC by Hennepin and Herman, 2008. That is a geophysics paper. It has been used for denoising, like random or coherent ground rule kind of things by Yarham, and this again UBC. Multiple removal, and some imaging works that done in the Colorado School of Mines and France. And I'm not going to touch this part, but I try to kind of see what are the basics for these things. So I look at their papers, and the emphasis was always on the sparsity. They were trying to show these things as sparse as possible. But I was still trying to look at I didn't have the picture. I wanted to create picture of curvelets. So what's the curvelet transform? Curvelet transform is an attempt, if you have a data, let's say M, and it has T and X, this is the seismic data in TX domain. So you try to decompose this data based on 4 factors: scale, angle, direction, or dip, we call it, and time and space. So these are like locality parameters. You try to go locally in TX domain and find the contribution of data to each scale and angle. I'm going to show this. This is a really simple concept in the FK domain, and you can see it how you can do that. So if you, the art of the guys in Caltech, don't know when, it was creating these atoms, these curvelet functions. When you create them, the only thing you will need, you just need inner product of them with the data, and you get all the coefficients you want. You're going to get like, this is kind of redundant transform. You're going to end up having more numbers, more figures at the end than your data that you had before. So the size of data is going to increase. It's going to make more, it's a redundant transform. So I usually put these things in, let's put it in simple word, I'm putting matrix notation. This is your data. This C is my curvelet forward transform. And by applying that one, I will get my coefficients. So these are like well-built and orthogonal kind of. The curvelet developers, they made these things to be really orthogonal, and like they call them tight frames. So if you had your curvelet coefficients, you can apply the adjoint or inverse, and you will get your model. So this is the matrix notation of those. Let's look at the FK plots here. So you divide your FK domain to scales. Each, you see this blue one is a scale 1. Scale 2, I'm not showing. Scale 3 is the green one. This is the 4, and this brown one is scale 5. And this the 6th one that almost covers 75% of your data is the finest scale. I mean, this is the scale 6. So you will try to see for each of these tiles, you divide each scale to small tiles, as you see here. And the task is to see how much of energy is contributed from TX domain to each of these windows. So that's all you want to find with curvelets, and they're going to show you how you can do that. So in order to plot them, can you see this? This is supposed to be, all right, that's maybe, I'm sure these should be having piles. Do you see the tiles here or not? Oh, okay, I think that when we go to the plots parts, they might show up. So what I did, these are like constant, like these are squares, like these are the size of the squares, each of them like 50 by 50. But the problem was, when you do the curvelet for this panel, it has different size than this one, different size. All of them have different sizes. So I needed to put them all in some one, like upscale or downscale them to something by 50 by 50 for presentation purposes. I wanted to show that, put them all in the same scale and see what I can see from the data. I hope I can see them later for my plots, but here, let's go for the data. So I make the synthetic seismic section and have 3 hyperbolic events, and this is the FK plot of that. So what I do, I overlay this is the curvelets tiling in FK. So you put in the top of that one, so I'm just showing that each of these tiles, what they're going to show. So you see, you have different kind of characters in each tile, and let's see how this works. Okay, it's showing something. These are squares, so you can kind of, this is the presentation problem here. So if I do the curvelets, this FK tile, you see the data I'm having events that with this slope on this side that I had here. You see the slopes in this side. It's kind of this is the curvelet panel of my data. See, all the data that have this slopes is going to be in this panel. All the data with this slope is going to be in this panel. And you see when the slopes are small, these are showing the slopes of the events, and these are for different scales. So I put them in these plots, and I can see that my data are kind of decomposed locally based on their dips. So this is kind of giving good understanding of this thing. You can see here, looks like this events here, we have the slopes here, and it always shows that 30 degrees. And I don't have any data at above 45 in this example. If you had a pure image of people, you might have all the data filled, but you see that in seismic data, we don't have data in the higher panels, and all of them are confined here. So let's look. Now I'm going to erase all the other panels that I had, scales, scale 1, 2, 3. They are gone, and I just keep scale 4. This is like this scale that's happening here. You see, this kind of works as a bandpass filter. Like I just get rid of the high frequencies because of the seismic data, but I don't have data here as well. So it's easily seen that I I did FK filtering. I did nothing. I did the curvelet, erase the other ones, and keep the scale 4. Come back to TX domain, and just from TX, I'm showing what happened with FK. I kind of erased all the other panels and kept that one, and that's what you see. What if from this panel, I just erased all of them and just kept one of them? That's what happened. You see here, I just kept this panel, this angle from this scale. And you see this is only showing me kind of the events with this kind of slope, like close to 15 degrees. And they are absolutely in here. The minus 15 is in the other side. But so you can see that. And there's a really close resemblance here. You can see this section here is pretty much close to what we see here in that curvelet panel. So, and look at the FK plot of this data here. It's exactly the window, and you made all the others 0 and just kept that one. You could have built a super redundant resemblance of curvelets by just doing FK filtering. But you will end up, each panel size would be having, let's say, 100 by 300, like TX size domain. But the art of the curvelet developers were to avoid this. They said, oh, why we need, for low frequency, we don't need that much a coefficient. We should keep less. And for high frequencies, we have more. So you can reach these curvelets by just going and just choosing each panel and 0 out the rest and gain the same things as what curvelets show. And this is the art of curvelets. This is the one that only frame operator can build for you. You just keep one coefficient here, and that covers all this area. And these are the common pictures that we have seen so far from curvelets. And they are like atoms that they have oscillations in one direction and like kind of smooth in other direction. So, and they related to this slope. So this have these slopes and this related to this one. Well, when I gained this picture and I realized that this curvelet's kind of decomposing my data for their local depths, I said, okay, what I can use for them, what would be the usage? So because I was working on interpolation and I knew the problems there, I knew there's aliasing, overlaps of the thing. So I thought, oh, maybe there's a way to show that. We did that, and it's accepted for geophysics. And if you want the thing, it's in here. This is the link that you can get it from online. But what was motivated me, because there were people in UBC, Herman and Hennenfeld, that they were using curvelets for interpolation, but they were using it for irregularly sampled seismic data. They were saying, if you have regularly sampled alias data, curvelets can't do anything. And they were saying, you can't reconstruct from the alias data. So I thought, oh, and they were saying, okay, based on that, they recommended, okay, jitter sampling. The recommendation was go and fix the acquisition stage. Try to sample more randomly than regular. But by this understanding that I get from curvelets, I said, oh, maybe there's a solution, and I'm going to show you how I came up with that soon. So the cornerstone for this work of interpolation was the classic work by Spitz, 1991, for interpolation, that he uses low frequencies to interpolate the high frequencies, get rid of the alias. And I was lucky that my supervisor, Mauricio, when I started my research, he pointed me to this talk, and I really understood that, and I've so far been able 2 or 3 papers to come out with different ideas from this paper. It's a classic work. And Colonnade used that one in FK interpolation. So the basic idea that you can go from low frequencies and get rid of alias in high frequencies. Low frequencies are not contaminated. So I combined this idea with the minimum weighted norm interpolation. It's like Fourier interpolation. Just instead of Fourier, I replaced curvelet coefficients in there. And I tried to come up with a solution for that. So this is the slide. So you have this data that you want to interpolate. This is your desired data. And these are the data that you have. These are related with something G, sampling matrix. This is like ones and zeros that eliminates some of the samples in M that gives you the data that you have. Simple equation. But you can have your interpolated data somehow related to the curvelet coefficients of data, with somehow modified with something I call it mask function. This mask function is going to eliminate some of the curvelet coefficients that I don't like. So I'm going to try working on this to see how I can build this W, the coefficients that I don't like, and I want to get rid of them. So this is the whole concept of this thing. All the contribution comes in here. After applying this inverse curvelet transform, I'm going to get data. So combination of these things is going to give me this least square. These are like Gm. Instead of m, I put this equation here. And you just have this cost function that related to curvelet coefficients. So what I'm going to do for that W, so I'm going to show you in plots better, but I'm going to divide my scales to two categories. The ones that they don't have alias and the ones that they have alias. So for the alias-free scales, I'm just going to do thresholding, keep high values in that curvelet panels. For the ones that they are aliased and the alias energy comes and contaminated, I'm just going to project mask function from the lower scales to them. With this in my mind, the dips should be having the same dip in the low frequency and the high frequency. This is pretty much the same conclusion you can make from Spitz paper. So let's show some example. The same example that I showed you. This is my data, original data, and FK plot. I decimated every three, like between each pair, I eliminated 3 traces. This is catastrophic. It's going to end up, you have this wraparound energy. So instead of this well, each panel has its own samples, at this point you just cut and everything wraps around and comes. And instead of having samples, now you have summation of the wraparound and the original ones. This is really hard. You have now summation of 2 numbers. How you can know what was the original number? You want to recover the original ones. And that's the trouble. And if you had 1D signal, that would be impossible. You can't get rid of the alias. But we're lucky we have 2D signal that even with our eyes, we see that the slopes are in this direction. But the alias shows me in the high frequencies I have a problem. So I can use the low frequencies now for that. So let's put back all those zeros between the traces that I eliminated. So instead of those 3 traces that I eliminated, I put 0 traces there. So what would be the FK plot of this? It would look like this. You're going to have replicas of this original spectrum that they come and overlay your original signal. So if you look at this part here, the blue box, there is no overlap of those the replicas with the original energy. So this is alias-free scale. But at this red trapezoidal area, you will see that all the signals from other replicas come and overlay your original signal. The task is how I can get rid of these and just keep the ones that they were original. So to do that, I put, again, the curvelet panel, curvelet tiling, say, overlay on the plot, and I notice this property. So I say, okay, at this point, at this tile, I don't have any alias energy. Anything I have there is the true dip. And they're supposed to be the ones, and they're exactly true. But when I come in this direction, these are having the same angles. So if I have the same slope in here at this frequency, and I should be having the same slope here, if my wavelet is not dispersive. This wavelet is constant. So I can say, okay, I'm going to have the same slopes here, but by assuming that one, I can get rid of the slopes that are coming from this direction and keep the ones that are going this way. And again, for this scale as well. So this is the main idea that I can use for that. So this is plots of that alias data. This is the curvelet plots of them. So until scale 4, you see it's like pretty much the same as the original one that I had. There's no alias. At scale 5, this high amplitude alias shows up. These are high amplitude, and it's like that's the problem that group in UBC they have. They can't eliminate this high amplitudes with just thresholding. And even in the scale 6, you see the same problem. These 2 scales are kind of contaminated with noise. So what I'm going to do, I'm just going to start making mask function from scale 4, keep the high values, and project it down. And this is going to be my mask function that you see. So until this point, I just did thresholding. But for scale 5, for these 2 here, I just project this one in here. I say, okay, just follow these slopes. And for scale 6 is the same, so I just project that one. And I ask my data in the curvelet domain, just keep anything that falls under this number 1 values. These are 1 and 0. So I'm just going to keep the ones that fall under that mask function. And that's what's going to happen. You're just going to get rid of all the artifacts that you had here. See all these things? By saying that, you just keep the ones that are under it. And if you look at the interpolation, it's going to be giving you the interpolated data, and all those overlaps that coming and overlaying each other is gone now. And this is the difference section. If you had, this is the original data, and the difference is like so low. Pretty much the synthetic data, but if I wanted to do it with other traditional ones, it would be really hard. I needed to choose the window size, chop it to the small linear sections, make sure that the linear assumption is satisfied. But with curvelets, they are pretty much locally built, so I didn't need to do all those things that we need with the traditional Fourier. So that I did for regular. This is the main contribution. What I did, like I just make this mask function that knows to keep which one in here just by showing the slopes in this one. By seeing the slopes in this one, it just says, okay, keep those, and you end up with this result. So I tried it for irregularly sampled one. And I pretty much gained the same understanding that the other people used curvelets. So I had this data, and I randomly eliminated 50% of data, and you'll see there are big gaps, some parts. They're like closed gaps, but it's irregular. It's a random choice of traces that got eliminated, and I put zeros. And this is the interpolation, and this is the difference section. It's a little bit different, but still the reconstruction was good. But for this one, as if you can see, this was the original, this is the missing data, and you will see there's this noise that caused by random sampling is so short amplitude. It's like you can see the structure under it. Structure is there, like this kind of data, you can see that. So by just doing some L1 norm, like they call it, keeping the high amplitudes, you might be able to recover that, and we've been able to do it. For this one, I didn't use the mask trick. I just went every single scale. These were the data. You see the amplitudes are small. Those amplitudes caused by those random sampling, they're too small compared to the original ones. So by just thresholding 2 or 3 times, I used iteratively weighted least squares. And I've been able to keep the ones high values and reconstruct the data that I showed you already here. And the reconstruction is reasonable, so I get rid of all those noise. So this is the basics of the L1 norm. That everybody was preaching the curvelets good for the sparsity because we gain lots of coefficients, we can get rid of them. We can get rid of most of them. So that was the basics, but it works only for irregularly sampled one. But like the whole point was that I was saying you can use them for regularly sampled one if you understand what they mean physically. So you can extract information from low frequencies to high. Another example, so I have still time here. I made conflicting dip events like that. I said, oh, that example is so simple, so let's make stuff that they are like going different directions and see how robust is technique. So I decimated again. This is my decimation, and interpolation is this. So you see this wraparound energy that comes in these sides. By the interpolation, you're pretty much gaining the same original data. And this is really complicated model as well here you're seeing. So what I did, again, I put 0 traces between my original one, and I make this FK domain of the 0 trace interlaced section. And these overlays, I see they never come and interfere with my alias-free section. So the alias-free is, I just find the dips from there in the curvelet and project the mask. And this is the curvelets of this alias data with 0 interlaced traces. You see these high amplitudes things coming in the scale 4 and 5 and 6. But it's until scale 4, everything is fine. There is no alias energy. So I can make mask function from this and project it down to the other scales and get rid of these high amplitudes that they are not supposed to be there. So this is the mask function I built from that, this data. And this is the result after applying that. You get rid of all those high amplitudes that come overlay your data. And that's it. So let's show some real data examples from always real data are challenging than synthetic ones. So this is a shot record from Gulf of Mexico. You can see like every time you see this patchiness in your traces, it tells you something. There's alias. By just seeing this patchy kind of things, this means there's alias there. And you can go to look at the FK, but you will see it again there as a wraparound. And when I interpolate it with the curvelets, I get this ones. You see this was the original data. And this is like nicely following all the events that I had. And this is the FK. This was the original data that the wraparound starts from here. And you'll notice that there is no signal above 0.25. So In the curvelets that I'm going to show later, I'm not going to deal with the scale 6. So I just going to, because I don't have signal there. So after interpolation, you see this is going to happen. This is all done in the curvelet, but I'm showing the FK plots. See, all this signal is pushed, and the alias energy is gone. This was the curvelet panels of my signal, that shot gather. You will see it's showing till scale 4, scale 3 here. The data is like going this way and like the original one. But after that, we don't have this much of slope in our data. These are all caused by the alias, by putting 0 traces there. So I made this mask function based until scale 3 is the original, and I project from scale 3 to 4 and 5. You see that even here, it's saying me that I have more positive slopes going this direction on the right hand than the left. The left, I don't have anything. And I see that in shot records. So curvelets like decompose my data. And this mask function that I'm building is based on just scale 3 and projected to the bottom scales. And this is the curvelets after eliminating those unwanted using this mask function. This is a near offset section example. So still this one has lots of complicated events like diffractions, is aliased events here. So I interpolated this one using curvelets as well. So you will see that there's like lots of events coming up, and it's 8 events, all of them coming back. There, I can detect some kind of leftovers of that patchiness, the atoms of curvelets in here, but compared to the fantastic job that they have done in finding the events and keeping the curvatures, it's been nothing. It's almost good. So this is the original data that I had, and it was aliased. And after interpolation, I added 3 traces between each, and I pushed it this much down, and the alias is gone, and pretty much that's what you get. Let's look at the curvelet panels of these. Now these are showing data at both minus and, you see the plus angles and minus angles. I see the data in all of them. But scale 4 and 5 unreliable because alias has already contaminated them. So I try to project again mask function from here to stably, to robustly reconstruct this alias scales. And this is the mask function I built from curvelets. And I projected, these are, you see, these are exactly the same projection from scale 3, 4, 5. They're pretty much the same. And by doing that, I just keep the signals that I know that they are original, and I get rid of the rest. Well, that was the interpolation part. So I thought that because I claimed there's going to be seismic processing in the past, I said, okay, I should make some other examples. And I tried to see if I can use them for ground rule elimination. So I needed to kind of change my mind from going from low to high. This time, I'm going to go from high to low, see how I can do that, if that doesn't make sense any. Well, I made this synthetic, you're just going to see the synthetic examples. I have this data, 3 hyperbolics, and I put this like linear events, like 3, 4, 6 of them, 5, with the amplitude twice the original data that I have. So these are my original data, they're primaries, and this one has like linear events, and they have the amplitude twice as strong as my signals. So you see, these are this is signal. It's like because of the resolution of projection, there's signals here as well. But you see the amplitude of this ground roll that I'm putting in here is way bigger than the original signal I have under. And also, it's wrapping around and coming and overlaying my original signal. If it wasn't wrapping around and coming to my signal, I can just cut these parts with the FK filtering, and I would get rid of the ground roll. But the problem is, these are so alias that they wrap around and come and overlay my signal. So what I did, say, okay, let's put curvelet panel again in this. It's supposed to be a little bit this way, but you can see there's no alias signals in here. I'm saying there are signals here in my synthetic, in my plot I see, but in here it looks like they're low. So I say there's no ground roll here. What if I extract information from these high frequencies and do the same projection I did with masks from high to low and see if I can get rid of this high amplitude overlay of ground rolls on my original data. So this is the curvelet plots of that with the ground roll. You see That's the scale that I'm talking about. I have, at these parts, no ground roll. It's in here. You see, this is scale. These are not, I know that these are ground roll, so I'm not going to pay attention. I just pay attention to these scales, that there is no ground roll on them. And I see that here. These guys are free. There's no ground roll on them. So let's make mask function this time from here and go up. So I make the mask function, keep the high values, and put the value 1 for them and the rest to 0. This is done easily. And I eliminate these 3 panels on the side because I know that they are not the signal that I'm interested in. 1, 2, 3. They are having signals, the ground roll. I am interested in these panels. And I make this mask function, and I just project from bottom and go up. And if I want to find the mask function here, I put addition of these 2. Any part that they cover, I make mask function here. These 2 is going to contribute to do this. These 2 to this, and up, like going till the low frequencies. And if you do this mask function, again, do the same least square fitting, this is what you're going to get. See the ground rolls that were in here, they are gone now. And this is the results. You see, now we see the data. This is better now. So the ground roll is gone. There's some little bit artifacts, but still, the result is gone. So the overlay of those ground rolls that are coming and overlaying my original signal, they're gone as well. So that's because of this nice decomposition that Curvelets been able to do, and I've been able to project a scale to a scale. If this is what would you get if you do ordinary FK filtering. So if you just cut, that's all you can do in FK. You can't do more than that. You can't just say, okay, can I get rid of these? So you're going to get rid of the signal as well. So I just put like that fan angle, like dip filtering, cut all those extra, but these are left here. And you will see these kind of common pictures that we usually see, the ground rolls left over. So, but if you will using curvelets and like you kind of dealing with both TX and FK at the same time, and you kind of trying to make connections between different frequencies by this projection masks. And with that, I arrived to my conclusion. So all I wanted to say here that the curvelet transform is local decomposition of data based on predefined scales and direction, can be conceived as an FK filtering combined with frame theory principles to obtain optimal and efficient redundant presentation of data. I said you might be able to do that, but you will end up super redundant by just keeping that part and having lots of zeros in the FK domain and going back to TX. You're going to have huge size of curvelets. But these guys in Caltech, they came up with a way to make all those orthogonalities that we have in Fourier work in the small scales and a small number of coefficients. But still, I'm saying curvelets are redundant. You still increase the size of your data. You're not going to end up the same coefficients that you have in your data. So for interpolation, what I did, from low frequencies, I extract the mass function. I knew that there's no alias in the low frequencies. I made my mass function, and I projected down to the higher frequencies and used some least square fitting using the sampling operator and mass function to reconstruct the data. So I'm saying in the irregularly sampled data, you don't need to do these because the noise, the alias that you have, they're low amplitude, and you can get rid of them. And for ground roll, what I did, I just changed the direction. And instead of going from low to high, I started from high frequencies that they don't have ground roll, and I tried to extract information from them to low frequencies. The acknowledgement, so I would like to thank Dr. Mauricio Saki for his supervision during my PhD program, and also after. I'm still enjoying discussions with him and lots of ideas. The curvelet authors at the curvelet.org, Candace, Damen, Donahoe, and Ying, they're providing their curvelet codes for, like, they're online, and you can do it for test anything that you want. And the sponsors of Signal and Imaging Group at University of Alberta. And with that, this is the end. Thanks a lot.